I would like to present Changjian Su, who will talk about equivariant K-theory realization of affine I quantum group. You will understand what is an I quantum group today. Let's thank the speaker.
Thank you. Yeah, thanks for the introduction. Yeah, first of all, I would like to thank the organizers for organizing such a wonderful conference and for inviting me to give this talk. Yeah, the title is about equivariant K-theory realization of affine I quantum group. So this is archive number, and this is also joint work with Weiqiang Wang. The goal of this project is to understand, to maybe construct some representations for this gadget called affine I quantum groups. But this is very unlike the usual quantum groups. This has not a triangular decomposition. So in particular, so the abstract theory for this construction of the representations is quite hard to generalize this I setting. And we all know there's a for the affine quantum groups, there's a geometrical way to construct the representations, and we want to do the similar things for this I quantum group. So the plan is the following. First of all, I will mention some construction in this equivariant K-theory. In particular, the convolutional algebras we use to construct representations of algebras. And second, I will mention some odd constructions of so this famous constructions used in this equivariant K-theory, Castellan-Rusty, Ginzburg and Vasserot. And lastly, I will talk about this I quantum group realization. Okay, so let me start with the basic. So the first part. So that's so we suppose we have a reductive group. So base field will be complex numbers throughout this talk. Acting on some algebraic variety x, x can be singular, and then we consider this abelian category, the G equivariant shift, coherent shift on x. So if x is smooth, we can just consider the G equivalent vector bundles, i.e., so the action on x leads to the action on the vector bundle, which is in a compatible way. And then we define this equivariant K group, denoted by Kg of x, just to be the Grothendieck group of this category. I.e., the objects are just isomorphs classes modeled out of this relation given by these short exact sequences. So since we throughout this talk, let's base change all this Grothendieck group to the complex numbers. So everything will be over C. So for example, so in the simplest case, for x is a point. So then this coherent shape, G equivalent coherent shape on a point is just a vector space with a representation of G. So in particular, so this will be just a finite dimensional representations of G. So Kg of a point would be just the representation ring, the tensor with C, let's say. So the representation ring of G. Okay. Moreover, so like equivalent cohomology, so equivalent cohomology of any variety is a module over a base ring. The base ring is equivalent cohomology of point. And in this K-theory setting, so if you have coherent shift and you have some representation, some G representation, you can form the trivial vector bundle over X, and you can tensor with such vector bundle. So then in particular, so this equivalent K group of any variety, so this will be a module over this equivalent K-theory of a point, i.e. over the representation ring of G. Okay? So when we talk about the equivalent stuffs, the base ring is always the equivalent K stuff of a point. That's all right. So then, what are the functors we have? Very quick mention. So to introduce convolutions, we need to know. So there are functors like push forwards. For the proper maps. And there are also pullbacks for, let's say, for example, for flat maps or for closed embeddings of smooth varieties. And also, there are tensor products. So the easiest thing of okay, so okay, let me mention very quickly. So first of all, so if you have a vector bundle, then we have this tensor product by this vector bundle. So this is for any variety x, and then as Ivan just mentioned, so if x smooth, so then we can consider this diagonal embedding, x going to 2 copies of x, and then we can define a tensor product on this smoothing. So using the pullback functor, so then this will define the tensor product. If you want to consider the singular varieties, then we need to introduce some pullback with support. Okay. So let me not go into the technical details here. Anyway, so we have these push forwards, pullbacks, and the tensor products. Okay. So the a very useful construction for convolution. So the setting is as follows. So this is used to realize algebras and also to construct representations of algebras. So let's say I equals from 1 to 3. They are smooth G varieties. So has G actions, and then let's assume we have Z12 G stable closed subvarieties. So because we are considering coherent shapes and push forwards is only defined for this proper push forwards, so we further assume this condition. So this let's say M1, M2, M3. So these have the projections denoted by let's say Qij to the factors Mi and Mj. So we assume this condition. So Q. So this Z12 we can pull back to this triple product, and the same for this Z23. And then we can see intersection in this ambient space. And then now we pull back using the third projection, the M1 and the M3. So we assume this map is proper when we restrict to this intersection of the period images. And then let's say the image of this thing, that's denoted by Z13. So then, and now you can imagine. So there's a well-defined map like this. So Kg of Z12 and Kg of Z23 going to Kg of Z13. So if you have shifts on Z12, shifts on Z23, so then we can pull back to this common intersection, and then we can take a tensor product, and finally we can push forward using this proper push forward. So then this will define some map that denoted by let's say star. Okay. So this is the general construction. So the interesting cases examples are the following. Okay. So let's say we are in the following situation. So let's chi is a proper map, G equivariant, and M is smooth, and N can be singular. So for example, the symplectic resolutions. Anyway, so if you are given such a proper map, and now so let's say what is M? We take the following examples of Mi. So let's say M1, M2, M3 are going to be N, and this is Z. Z12 equals Z23. Let's say this paper product with itself. Okay. And then it's very easy to see. So all these so then this will be also equal to Z13, and now let's denote this by Z. So all these Zij, they will be the same if we take this Z12 and Z23 to be the self product. So then in particular, so then that construction then gives a product on the equivalent K-theory of Z. So this so then this turns out this is an associative algebra with the unit, the diagonal class. So this is the mechanics and to realize the algebras geometrically. And then to construct modules, we use the following setting. So now we take M1, M2 to be M. But for the third guy, we take that to be a point. So and now we choose some point x in this packed space N, and then we let Mx to be the fiber. Okay. So and now we take Z12 to be the same as before, the fiber product. But we take Z23 is to be M of x. So this lies in M2 product with a point. So this Z23 is just the fiber over this point x. So then that construction gives then this K. Okay, then it's easy to show this Z12, Z23, and then Z13 is the same as Z23 is the fiber. So then that construction gives a map like this, Kg of the fiber going to Kg of the fiber. Okay. So and now by the first construction we know this is a associative algebra, and then by the second construction we know the K-theory of the fiber will be just a module over this algebra. So that's how we use this convolution to realize the algebra geometrically and also to construct some modules for this for this convolution algebra. Okay, so this is this convolution algebra. So this is a K-series setting. You can imagine there is also a story for the homology. Okay, so that's the first part. Are there any questions? Yeah. 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 M. Yeah. Yeah. M3 is a point. First of all, Z13 lies in M1 and M3. So M3 is a point. Yeah. Okay. Great. Yeah, thanks for the question. Okay, so this is the basic setup people are using again and again in this geometric representation theory. So that's very old, dating very old to So the second part, some very old constructions in this field. And this technology is also used recently by BFM, Berman, Finkelberg, and Nakajima to construct these Coulomb branches. Anyway, so the first, Castell, Lucic, and Ginzburg, dating back to 1987. So this is also mentioned in Penghui's talk this morning, and also mentioned in Basil-Campbell's talk last week. So for simplicity, let me assume G is simply laced, semi-simple. So fix a Borel subgroup. And let me use this curly B to denote this complete black variety G mod B. Now we want to apply this construction to this most classical example of this symplectic resolution, i.e. the Springer resolution. And then we consider the quaternion bundle of this black variety. So this will be a symplectic variety. Of course, there's a natural action by the left multiplication of G on this black variety. So in particular, this induces action on the quaternion bundle. And then so this is symplectic, and we can consider the moment mapping to the dual of the Lie algebra, and we assume this is semi-simple, so the same as the Lie algebra G. And it's easy to show. So the image of this map actually lies in this thing called this Neapolitan cone. So we shall talk about this in this morning. And this turns out to be, okay, so let me use the same name mu. That's it. So this is a resolution of singularity called this Springer resolution. Okay. There's more symmetry on this quaternion bundle. There's another action of this C star by dilating the quaternion fibers. It acts trivially on the zero section of the flat variety. It only acts on the fibers. Okay. So in particular, so if we just apply this, the first example of the equivalent case of a point, for the C star equivalent case of a point is the representation of C star. So then this will be just a drawing the functions on this C star, so i.e. the Laurent polynomials ring with one variable Q. Okay. And why this equivalent case here has applications to this representation of quantum algebras or maybe affine hack algebras. So this is a very remarkable observation of Lucic. So the equivalent case of a point, there's a Q, and that Q is responsible for the Q in the quantum groups, and also responsible for this Q in the hack algebras. All right. So and now so this will be our n, and then this Neapolitan cone, this curly n is our n, and then we form this Steinberg variety. So since I'm going to use several different Steinberg varieties, let me just use VBB to denote this one. So quaternion bundle, the flat variety, the fiber product with itself over this Neapolitan cone. So then this first the example tells us. So then now we consider the G cos C star equivalent K-theory of this Steinberg variety. So then this is there's a convolutional algebra structure on this. So this is an algebra constructed geometrically, and now we want to introduce this purely algebra, this affine hack algebra. So this is also mentioned in Pengwei's talk this morning. So there will be affine Hecke algebras and affine quantum groups and affine quantum groups. So the easiest relation I can write down is for this one. So I'm only going to write down the relations for this algebra. So okay. So this affine Hecke for the dual group. So AIII. So algebra generated over the base ring is over the equivalent, the Laurent polynomial ring of one variable, and the generator is E lambda TW. So W is inside this finite well group, and lambda is inside this character lattice. Model of some relations. The relations like and also these Breda relations for these generators, ESI. So this TW will form this finite Hecke algebra. And then this E lambda and E mu, they generate a ring, the equivalent case of a porous equivalent case of a point. And the interaction between them is something like this. Yeah. And so this, okay. So this is so this is okay. So this of course there are different presentations, and this one is called this Bernstein presentation. All right. And the result is the following. So we have this geometric constructed algebras, convolution algebra, and then we also have the Steinberg Ginzburg. So there is an algebra. There is an algebra isomorphism of this convolution algebra of the Steinberg variety for the coordinate bundle of the flat variety with this affine Hecke algebra for the dual group. So this is a very old result. Some remarks. First of all, so this geometric realization of this affine Hecke algebra, this leads to and now you just use the second construction, and there's also some more work. You can use this to get a complete classification of the irreducible representations of this affine Hecke algebra. And this is the so-called the local long-length conjecture, the terminally ramified local long-length conjecture, or maybe the Berlin long-length conjecture. And the second remark, so last week we heard the talk by Roman and also mentioned by Penghui this morning. So this is this isomorphism is categorified by some counterclause. Okay, yeah. Okay, yeah, that's another presentation, yeah. Okay. All right, yeah, so this, so of course, this is a very famous construction. Let me very quickly mention another one. So this Ginzburg, Vasserot. This one will be more related to our work. So the setting is as follows. So here we consider the complete flag varieties, and now so they replace this complete flag variety by this partial flag varieties. But now we have to restrict ourselves to type A. So partial flag variety in type A. And we want to fix two integers, n and d, that's equal to 1. So the d is the dimension of this ambient space. Okay, so now we consider this flag. So which is for so this n step partial flags in the ambient space is the d-dimensional vector space, and this n is just the number of steps. So i.e. So sequences of vector subspaces in this C of D. And so then this will play the role of this curly B in the previous story. Now we consider this M to be the coordinate bundle of this partial flags. And sorry? Oh, yeah, thank you. Oh, we don't. This is a disconnected variety. Yeah, we don't. Yeah. Yeah. Thanks. And now, similarly, so there's an action of G. So now, okay. So then there's a action of this G of GLD acting on here, and now we do the same thing. So this is a symplectic variety, and then we consider the moment map into the image wheel again. That's in the Neapolitan cone for this GLD. Okay. Okay. And then now we use this Z of A to denote the corresponding Steinberg type variety, and so this has a okay. So this also has an action of C star acting on the coordinate fibers. And now we by the first construction I just erased here. So again we will get some convolution algebra like this. And what would be the what is the algebra behind this? And so this precise. Which two actions? Yeah, this is a scaling action, scaling the coordinate fiber. Yeah. Okay, so the algebra is the following. So then this would be this quantum affine algebra for this GLN. And now here comes this n. So this n step. So n step, then we get the algebra GLN. Let's denote this algebra by U. Okay. Okay, I think everybody can find a presentation for this algebra in any quantum group textbooks. So let me not write this down on this blackboard. So anyway. So you just consider the affine thinking diagram of type A, and then to each vertex you have this and to each vertex you have these generators EI, FI, and KI. So this is for this affine thinking diagram. So n-1. And then you can. So this is okay. So this is the Ginzburg presentation, and then you can imagine there is some relation between these generators, and there is also a there is also another this is there's another presentation. So like in the for the affine Hecke algebra, there's also this Coxeter presentation mentioned by Yuan, and now this presentation over here is this Western presentation, and for this quantum affine quantum groups, there's also another presentation similar to this Western presentation called this Dreamfield presentation. And now for each vertex in this corresponding finite type quiver, we have this EIR, FIR, AIR. Anyway, let me now write this down explicitly. Okay. So Ginzburg and Vasserot. So they prove, but unlike for the affine Hecke algebra setting, here we only get there's a morphism of algebras. See from this affine quantum group going to this Equivariant K-theory. Okay, so and if T, okay, so this since I'm okay, maybe let me just say Q. So this parameter is that the quantum parameter is also denoted by Q. So if Q is not a root of unity, and now we can specialize. Okay, maybe let's say T. T is some number in C star, and now we can specialize this this algebra homomorphism to T, i.e., so this means set, and then now you say that Q is let's say Q is a formal variable, and then you say that Q equals to T. T is some complex numbers, but then this is a surjective. Okay. We don't know. Yeah, unlike this one, yeah, we don't know. All right. Yeah. So all these two constructions, they are quite old, as you can see. So then we can ask the following two questions. So there's natural generalizations of this. There's in the two directions we can generalize. Okay. So first the direction is, so here we consider the quantum group for GLN. So we can replace this quantum group by quantum affine algebras for other Lie algebras. Okay. So this is associated to GLN. We can consider the other quantum affine algebras maybe in the simply less case, and it's well known. So this is okay. This is achieved by Weiqiang Wang is quiver variety. So we know, so this variety, this cotenary bundle of this Einstein partial flag variety is a example of this quiver variety. L. So this is Einstein, and I mean this D is the quiver variety of the following quiver, is the following dimensional vector. So it's a type A quiver, n minus 1. And there's a one Fermi vector, double the agent. So the dimensional vectors is here. We put the D in this first Fermi vortex for this first vortex, and in the following we put Vn minus 1, Vn minus 2, V2, and V1. Okay, so this is small v. So these small v's are just the dimension of those corresponding vector spaces. Okay, and now you see. So this is if you ignore this, then this is the type A equivalent, and then now you can do this for the other AIII equivalents. And you can also use that to construct the corresponding representation to study the other quantum affine algebras. Okay. That's a very good question. So we can, I don't think we can do that using, but there's a very recent work of Vasserot and Verona using this critical convolution stuff. Do something. Okay, and then the other, okay. So this is so the first question is about looking at the source, and now we can look at the target. So this is ZE. So if you replace, we can replace. So this is Steinberg type variety. So we can replace this by Steinberg type variety for the other classical groups. And we wonder what is the algebra behind this. Okay. Yeah, I'm going to talk about that soon. Yeah. Okay. Okay. I think yeah, these are two natural questions. But I think once so this is around 2003, something like that. I think when the Ginzburg found this, and maybe people lost the interest about the other generalization. Okay. Anyway, so let me mention some. So there is some work recently done. Some work done by another group of authors for the finite type case. Fine job being Ma Hao and Xiaofu Silan. Okay, anyway. Okay. So okay. And now the faster path. Okay. So and now we want to study this question. So we replace this Steinberg type variety to the other classical groups, and we want to know what can we get. Okay. And this is related to this. Okay, I will try my best to say something about this iPhone group. What is this? Okay. So, but before going to the algebra, let me very quickly mention this geometric setting. So the geometric setting is as follows. Now we consider flags of type C. Now we fix. Again, we fix D and N, and this capital N is this 2N. Now we use this GC, this symplectic group. We need to be very careful about this which group. And now we consider the partial flags in type C. So then, as before, this the sequences of subspaces, vector subspaces inside this two-dimensional space. But now we put this is type C flags, so we put this condition n minus I orthogonal. So this is orthogonal. This is with respect to this symplectic form on this 2D-dimensional symplectic vector space. And now we have this cotangent bundle. And also this moment map going to this Neapolitan form of type C and this ZC. Everything is the same as before. Yeah. Just add C everywhere. So this will be our geometric setting. Our GC equals C star. Okay. So this is the geometric setting. And now let me mention something about this algebra. for the icon group. So first of all, so this is also known as quantum symmetric pairs. So then what is first of all symmetric pair? Symmetric pair consists of the algebra G over the complex numbers and some fixed points of algebra. So G is over the complex numbers, and the theta is some involution. Okay. For example, G is SLNC, and I say theta is minus transpose. So then this is G theta, if you can imagine. So this would be just SON. Okay. And so these stars, they are these symmetric pairs. There's a classification. This is classified by something called Satake diagram, which is a generalization of this thinking diagram. This consists of some diagram with an involution. So this tau is a diagram involution. I will give one example later. There is a complete list for this, and you can find it somewhere. And you can imagine, so this quantum symmetric pair or this I-quantum group is just the quantization of these symmetric pairs. A quantum symmetric pair denoted by, let's say, U and UI, some UI is something like this, such that, so this U is a quantum group, so then we have this coproduct. So if you restrict this coproduct to this UI, then it maps, then the image will be like UI times the U, IE. So then this is a co-ideal subalgebra. So this UI is a subalgebra of the whole quantum group, and then the image under this coproduct has to satisfy this condition. So this is a co-ideal subalgebra. Okay. And people call this thing called this this is the I quantum group. I call this. Okay. I can only say very little about this. So if you consider, so in this classification, so these diagrams, there's something called there are two kinds of dots. There's something called white dots, and disjoint union, some black dots. There are two kinds of dots, and if there's no black dots, then they call this is a quasi split, and if moreover this tau is identity, they call it a split. So let's assume in the quasi split case, so i.e. this black dot is empty. So then this thing, this UI is generated by this generators bi, ki, k tau I inverse. So this ki is the generators for this original quantum group in this Ginzburg representation, and this bi is something like this. So it's fi plus some parameter theta I we need to choose, and the e tau I, and then ki inverse. This theta I is some parameters we need to fix when we define this thing. Okay. That's right. Yes. Yes. So you just do this thing. So for for each vortex I, even including that affine vortex, we define a generator like this. Yeah. Yeah, this is simplest case. And if there is a black vortex, so then here they further act by this longest element, this affine braid. There's an affine braid group action on this quantum group, and then you act by this longest element in the affine braid group for this black for the black vortices, so the subdiagonal. Yeah. That's more complicated. Yeah. So I'm just saying, so in this classification, so this each vortex has a color. It's a white or black. There are two kinds of vortices. Yeah. So that the simplest one is so you choose you choose a water AY thinking diagram, and then you choose another copy, and now there's this tau. You just switch them. So then this called this diagonal type, and then now this U would be just the two copies of the quantum group, and then this one would be just the usual quantum group. Yeah, that's the simplest one, right? Yeah. Okay. Yeah, anyway, so that is to say, so the usual quantum group is a special case of this I quantum group. And Weiqiang and his school generalized many constructions for the usual quantum group to this I quantum setting. Okay. And now, so the geometry is here, and the algebra behind this geometry is given by this Steinberg diagram. So this one. There's no all of them are black. All of them are vector vortices. And this tau is just the switch. This horizontal vortices. Okay. Okay. So this is these are tau. Okay. So take that one. And now and then there's by this construction there is some quantum group as all they are. So this is all. We can only do this case. Yeah. 你放头哦。Theta. You mean this theta? No. No, I will project first. Maybe I should just introduce this algebra first and then introduce this geometry. Okay. Yeah. That one is only responsible for this one. Okay. So then this gives some algebra. Let's say U tutor I. This affine case. So that's the tutor. Yeah. This is a horrible thing. So there's a recent work also this year by. So this Lu Ming, Wang Weiqiang, and Zhang Weilai. So they found a dream field representation. For this quantum group, and now so as you see, in this these two constructions I told earlier. So for this Steinberg-Ginzburg story and the Ginzburg-Vasserot story, we always need this dream field representation or maybe the burst representations to begin with. So then, if you are interested in these relations, you can find in the paper. It's very similar to the usual quantum group, but there are some differences for these spatial vortices, which is fixed by the involution. So anyway, then the main result is also this here. So there is similar, but there is an algebra homomorphism. As everything that's the either C and also either GC. And similarly, if T is not a root of unity, so it's really similar to this type A story. I said CT is subjective. Okay, so then, so remark. So actually, in fact, there's more difficulty. So localization is needed. Let me for this to work. So this is another very nice. So for this generator, the correspondence for this generator, there is some issue for that one, and we need to localize to make things well defined. Yeah. Exactly. Yeah. All right. And all this, and you can imagine all these constructions is almost the same. Just find out the suitable correspondences for these generators, and then you take the relation. Okay, so then this is an algebra, and now let me mention very quickly why this is useful. Why now? So there's something Ginzburg classification. Okay. So let's go back to this general setting, this mu of n going to n, so which is a proper map, and M is smooth as before. Or you can do it. You can do the equivalent setting. Okay, J is the fiber product. So then it's easy to show. There's something called the Bragg-Moore homology. Bragg-Moore homology of this Steinberg type variety. There's a shift theoretical interpretation of this. So you can write this as the extension algebras in the bounded derived category of constructor shifts on this target space n, and the type push forward of these constant shifts on n. Maybe this. Okay, if you need to get a graded isomorphism, we need to be very careful about this grading, but you can make it anyway. All right, and now, so this is the first thing, and then you come back. You use the decomposition theorem for this. So if you know the decomposition, then, but this is usually very hard. So we can decompose this into some simple power shifts, tensor with some. So then, okay, so this is some vector spaces, finite dimensional vector spaces, and this is anyway some simple power shifted simple power shifts. And now if we let L phi to denote the summation, the product over these multiplicity spaces, so then the result of Ginzburg says. So then this L phi, as phi runs over in this data. So then this is a complete list of isomorphism classes of simple modules for this convolutional algebra. Simple module. Okay. So AIII. So this so as I said earlier, so this a Bragg-Moore homology has these functors as in the Weiqiang K-theory. So then this is a convolutional algebra, and then we can realize this using this shift theoretic language, and then we combine with this decomposition theorem, then we can get a complete classification for the simple modules of this. And this is how Kasdan, Lustig, and Ginzburg they use this to prove and combine with the geometric realization to give a complete classification for the affine Hecke algebra. Okay, but this is as you can see, this is a homology case. Then to use that to get a representation for this I-quantum group, then this is the Equivariant K-theory, and then we need to go to the Brammer homology first. And you see, so we need this surjectivity because if we start with some irreducible module here, we want to pull back to this I-quantum group. If we want to say this is still irreducible, then if this is surjective, then we can say that. But that's why we need this. Okay, this is technical, but let me. Okay, so let me just mention this. Then you can just read Chris Ginzburg. So there is an algebra homomorphism from this. Okay, so now let's go back to this setting of this type C container bundle flags to the Neapolitan count. So and then PC this. Okay. Anyway, there is a sequences of maps which you see. Okay. Okay. I need. So this is a okay. So the base ring of this K-theory is just always the K-theory of a point. Oh no. The tensor with the base ring, but then we need to specialize. So A is some semi-simple element in G and C star, and then now we just specialize this K-theory to that, and then now here comes the fixed point. So anyway, so there is some map which will preserve, which will compatible with the algebra structure. And now you can use this to and now you can use this, and then also this general machinery to construct some representations for this convolution algebra. Okay. So in particular, simple. There's a simple representations like simple representations of this type, but this is usually quite hard, and also some standard representations of the cohomology of the fibers. And there also by this very general machinery, we know the multiplicities of these simple modules inside these standards. But okay, anyway, so then we can construct geometrically some representations of this I-quantum group. Okay, but unfortunately, so this is very hard to say exactly what are those representations. Anyway, okay. So then the last study, if we combine this story with this Carson and Lucy Ginzburg story, then we have the following duality: the Schur-Weyl duality. So recall, need a big blackboard. So this U tilde maps to the Steinberg array of type C, and now so this is okay. So MC was NC MC. Now, so we can have something in middle, MC, NC. This is the partial flags, and now here we can put the complete flags here. And now we can also take this, let me just write K equivariant to denote the G cos C star equivariant. And now if you apply this, the first construction I wrote over there, so Z12 equals this, and Z23 equals this. And then you can check J13 will also be equal to this. So then in particular, so then this will construct action on this space. And similarly, you can do the same thing. You can just put this complete the Steinberg variety of type C for the complete flag varieties. And we already know, so then this is the affine Hecke algebra of type B. So then this also action on here. And we know, and by the natural construction, so these two actions, so they commute. Which is so where type thing, but we cannot prove they are double centralized of each other. Okay, I will stop here. Yeah, thanks. Yeah.
So what happens if you use orthogonal groups instead?
That's a very good question. So, Weiqiang taught me. So then we may get the very similar type algebra, which is also associated to this same Satake diagram. Yeah, but which I don't understand why. Yeah, if you replace type B or type C, we may get the different things. Yeah. It's not like unfolding related to this unfolding. Yeah.
Not an evolution, but something like these three.
Which one?
The theta that you use.
We have to start with the evolution to define this symmetric pairs, quantum symmetric pairs. Yeah, we need to start with that.
So following Professor Yan's question, so I'm not sure if theta comes from some certain automorphism to the distinction diagram.
Yeah.
If it does, then for example, D4 have S3 automorphism.
Thanks. Let's go.
Yeah, other possible theta so that you can fold the other kind of sort of some kind of folding.
Yeah.
That possible to start with.
Yeah. So I asked Weiqiang about this, but he says at first I thought this may also be I thought this may be related to this unfolding folding stuff, but he said this is not, which I don't understand about this yet. Yeah.
What you said have a categorification?
Categorification? That's another very good question. So so recently there is a generalization of Roman's story to this parabolic setting by I think Dylan, Dylan, and Harrison Chen and W. Dylan. Yeah, there's some story going on. Yeah. So if you one is if one group is brown, one is a parabolic. So this is done by Ivan and Roman. And then if you P and Q, so then this is from the Chen and Dylan.